My name is Sergey Polzunov. I work for RipeNCC in Amsterdam. And I wanted to describe how our data processing backend works. How many of you know what RipeNCC does? Okay. And how many of you know what Atlas project is? Okay. I have a few intro slides. RipeNCC is a non-profit organization. It's established in 1992, and right now it's shifting its focus to developing services for community. One of these services is Atlas project, which is designed to measure infrastructure in the internet. So we have probes which are deployed all over the world. They look like that, and they measure websites, hosts, and they have measurements between themselves. There are almost 7,000 probes all over the world. So you can see that some of them are red because they're offline for some reason, and the highest density is in Europe. But right now we're trying to deploy probes in some far regions all over the world. So there were 3 generations of probes. The first one was the smallest one, and right now they are a bit bigger. I have some of them to distribute, so if you don't have one and you want one, you can come over and take one. You just plug it into Ethernet and attach power, and you're good to go. The probe will start doing measurements instantly. The probes also have anchors. Those are these bigger boxes. These anchors gather measurements from probes and stream them to our servers. So there are a lot of sponsors who host anchors, and they get more benefits from the measurements. So if you want to host an anchor, that's you should also talk to me. Some stats about the network: 7,000 probes, a lot of active users. There are built-in measurements that are pre-configured, and there are also user-defined measurements. So user can create measurements on the website if they want to send pin requests, for example, or do trace routes, or do DNS queries. Yeah, the goal till the end of 2014, get 10,000 probes. Yeah, the biggest density is in United States and in Europe. So I wanted to talk about the pipeline. So we have all these measurements happening all over the world, and that's a lot of data. And that data we accept in our queue service, and then we store. And we need to power the website, atlas.tribe.net, which have the dynamic views, maps, graphs, all of that. So we need to store this efficiently and then stream, reply to queries from the UI. So we have something like that. From left to right, you see the probes. They are talking to Atlas controllers. There are only 25 controllers. Some of them are, I think all of them are in-house, actually. So they accept the measurements from the probes, and they push them into the queue servers. And after that, our cluster takes over and consumes measurements and inserts them into HBase and Hadoop. Have any of you worked with Hadoop and HBase? Okay, cool. So you know what I'm talking about. So Hadoop is a clustered, HDFS is a clustered file system, and HBase is a key value database on top of that. It's designed to work with a lot of data, big data, and it's supposed to be really reliable. We're going to move from left to right in this presentation. So first, controllers, they are custom code, basically just accepting measurements and streaming them to queue servers. Nothing fancy there. The probes are smart, so if the controller is down, they will talk to a different one. so they can migrate from one controller to another, and we can redeploy them easily and deploy new ones. So it's pretty nice. Then they push them into the queues on the queue server. We have 4 queue servers, which are basically big machines, really beefy machines. They're not connected in a cluster, just for different queue servers. And controllers also will, if one queue server is down, they will talk to another queue server. The queue server has different queues for different clusters because we have 2 production clusters to allow us to do upgrades and stuff. It's yeah, it's like that, like hot swap. So one cluster is production right now, and another one we're consuming data there and updating data sets, but it's not production. So then we just switch record in DNS, and all the requests go to a different cluster. We receive almost 2,000 measurements per second, and it's growing. And users creating new measurements, and so this is growing. And this is the graph of monthly data. The size of the data set per month. So you can see that in 2014, it will hit, I think we already hit 1 terabyte per month. So almost a year ago, it was only half terabyte. So right now it's 1 terabyte per month. And you can see that blue color, it's the DNS queries, because they're heavy, they have big responses. So that's a big part of the data set. There are smaller ones like SSL certificates, and you can't even see the car almost. Cluster. We have 144 machines, Dell boxes, PowerEdge C5000. They configured as 110 workers. As I said, they're powerful machines. We have 4 terabytes per machine, and we have quite a lot of RAM because we're running HBase on this cluster, and HBase is really hungry for RAM. So we got boxes that can handle that. Usual configuration: 2 masters, 1 bastion host. Bastion host runs scripts and allows user to talk to the cluster. Basically, it's like a protection. And journal zookeeper nodes, that's for internal Hadoop and HBase housekeeping and configuration. On a software layer, we have a really nice configuration, I think. Pixie boot configuration, so the boxes get their image from the server, and they keep the root file system in memory. So it's really nice if you want to reboot the box. It's just fine. It will reboot, download the updated image, and it will just work fine. It's managed by Ansible playbooks, which is also pretty nice, Python-powered playbooks. And we use vanilla distribution package from Cloudera company. Basically, the Cloudera just takes trunk and applies patches to it and tests everything, and then they release the package, which is supposed to be tested, stable, and reliable. Yeah, that's the software layer. Just to remind you the pipeline. So right now we're there on the cluster. So the queue servers, they have data, and then the cluster takes over and consumes measurements. Consumers, there are just Java daemons that consume measurements from the queue, and so we have a huge stream, and we insert this stream into HBase directly to update the tables, to have real-time updates for the website, so user can see the latest measurements or some latest aggregations. And also we stream those measurements to HDFS for some batch processing, the jobs that run once a day, once an hour, and for backup, basically. So we want to store all the measurements in files because we don't trust HBase that much, so we prefer to have files. Batch processing. So when we have the files on HDFS in the clustered file system, we want to do some aggregations. We want to calculate some statistics. So we run big scripts and MapReduce jobs. Previously, that was more MapReduce jobs, but right now we migrated all of the logic to big scripts. Big is really nice for doing this kind of data processing. Raw data size is growing, so right now it's even more than 5 terabytes. I think it's even 6 terabytes. But that's just raw files, compressed raw files. Because we have all the data sets in HBase, these batch processing jobs, they create H files. That's internal format of HBase, so it's really simple to insert those files into HBase really fast. It's like bulk input. That's how we update HBase with aggregated data sets. HBase, big database. We have one huge table, which is 30 terabytes, and 8 small ones. So one huge table is basically all the measurements we have. And they're indexed by different fields. So users can, on the website, they can ask for a random interval in time and ask for raw data. And then we will stream the data from this table to them. And smaller tables, they are aggregations and some derived data sets. So that's a really important point, that if you want to have fast tables in HBase, you really need to denormalize and pre-compute as much as you can in batch processing and store. You would have to store data a couple of times. Yeah, so that's 8 small tables are mostly aggregations and some pre-computed data sets. Tables are really important. So as I said, the table structure and is really important. That's why we pre-compute and denormalize. We try to build tables for use cases. So it's not like you build a table and then you think what you can query, how you can query it. It's first you have a use case that you want to reply to this query really fast. Then you think how you're going to store it. So we have really smart index structures with complex keys that allow us to do scans, to do just read one time and not send multiple queries. And also we use a neat trick with HBase, server-side filters. You can create a piece of code that HBase will run as close to the data as possible on their servers. So if we have 100 region servers, the HBase will distribute this code to all of the workers and run this code as close to the data as possible. So you can filter out data, you can tweak it. So that's really nice. You don't have to download everything, filter out, and then stream to the client. You can do it on the server side, on the region server side. So when we have these nice tables, we use it to power the website. You can go check it out. It's atlas.drive.net. It's a normal UI server. It runs Django, and it talks to HBase through our Thrift proxy. If you know Thrift protocol, it's very nice. You can create complex queries. So we use that to communicate with HBase. We added a couple of patches and tweaks to the vanilla HBase Thrift server. So we run our own code. And the Thrift servers are stateless. So they are perfect proxies. And we can start as many as we want. And if one goes down, the UI will just talk to another one. This is one of the examples of what kind of views you can get from the raw data. So Atlas does measurements between probes, and those probes are probe 1, probe 2, results of the measurement X. And we need to process them, aggregate it, and this is one of the use. It's called DNS mode. It's basically DNS queries against root server. I'm not sure if you can see it. It's against root server. So this is the colors are the response time aggregated by I think 10 minutes at this level. And you can zoom out and zoom in. So you can, if there's a problem with connectivity, you can see it. You can see it here. Another example would be this graph. It's the graph of the ping response times. So the red color is lost packets, and the spikes are spikes in response time. So there was actually a use case when you can see that something is happening with your infrastructure if the response time goes really up, or you can see a lot of red color, so you know that something is happening. And this is an aggregated view from the raw data. This is another one. This is location-based. So for Ukraine, for example, you can see which root servers the probes in Ukraine are talking. For example, for Ukraine, it's sometimes it's L root, and it's different root servers, and you can see the response time. So the red one is the bad one. So there are some probes in central Ukraine that they don't have good connectivity. And that's what we have right now. And there's a new neat thing that we just developed a couple of last weeks. This is the system that allows us to stream measurements to clients without HBase, just bypassing HBase and Hadoop. We read messages from the queues and stream them through WebSockets to the web clients. So users can subscribe to one probe ID or measurement ID or measurement type, and they'll get all the measurements from our system. This example shows the DNS measurements against different instances of K-root DNS server. We have a lot of instances deployed worldwide. Some of them are in Tokyo, in London, in Amsterdam. And different probes all over the world, they talk to the closest one. They try to talk to the closest one. So this is aggregation by 10 seconds. So you can see that in Amsterdam, there are quite a lot of probes. The bigger the circle is, the more probes are talking to this server. So because measurement is scheduled every n minutes, you can see the clear lines when the measurements are executed. The color is average, I think it's mean response time. So for London, for Tokyo here, it's really red because of the routing. The hoster that hosts K-root server in Tokyo, I think he advertises his prefix with really short path. So probes from US are going to talk to Tokyo. Probes from West Coast are going to talk to Tokyo. So the statistics, you can see that response time is bigger here. That's why it's red color. And the lines here, these are probe migrations. So if the probe at that time was talking to this server, but with the next measurement, it was talking to another instance, we'll draw a line here. So that's really nice if you want to see how the routing changes over time, and if you want to monitor in real time what's happening. We had a maintenance on Amsterdam K-root server, and we brought it down for a brief period of time. And then we saw how probes were migrating. There's a post on the right website where you can see the video. This is speed up. So you can see that instance becomes available, and all the probes are starting to migrate there. So there are slow ones that will migrate there a bit later when the routing changes. But you can see that circles are growing, so more and more probes are going there. And that's really nice if you want to monitor your connectivity or your infrastructure in a way. Because these are just measurements from Atlas project. That can be your measurements or built-in measurements or whatever. So after a while, when the instance is online and stable, we will not have any migrations. That will just stay like that. This is it. That's what I want to share with you. Sorry, that was really fast-paced and maybe a bit drafty. But anyway, if you have any questions. Once again, I have some probes, so if you want to try it out or take one, you're welcome. Nope. Try.
Yeah? Okay. Thanks for the nice presentation on this. My question is, you mentioned that you're currently feeding about 2,200 probes measurements per second.
Yep.
Is this per probe or something?
No, it's the whole stream.
The whole stream.
Yep.
So, what kind of measurements the probes take? Is it per minute, per 30 seconds, something?
Okay. Measurements are usually scheduled every 3 or 5 minutes. So yeah, those are DNS measurements, DNS requests, pings, trace routes, SSL certificates requests, and yes.
Okay, thanks.
Thank you for the presentation. I would like to ask, how do you measure the SSL certificates in this communication while you are the third party here? As far as I understood, if I can plug this probe somewhere, how the SSL measurement will take in place?
You can configure it on the website. So when you attach the probe, it will get the list of pre-built measurements. Basically, it will talk to different probes, and it will run some of the measurements from different users. And you can configure your own measurement. Regarding SSL certificate measurements, I don't know a lot of details about that, sorry. Exactly how you configure the measurement and what will it get. Because I work from a data perspective, so to me it's just another data point. But if you go on the website, you'll get more information about that.
Okay, thank you.
Yeah.
Hi. Interesting lecture first. Second, what about the BGPmon and the RootMon projects? Are they also fed by the Atlas?
There is a new version of BGPlay, if you saw it.
Yes, thanks.
Yeah, and that's kind of, it's using HBase Tables as well. There is a new project that will replace, I think it's in development right now. It's just starting, we're prototyping. If you know RIS project, the old RIS.net. Yeah. So there are different boxes deployed in exchanges all over the world, and they gather BGP dumps, the whole routing table, and they also gather updates. But they do it in a stupid way. They kind of dump those updates in a file, and then we sync those files once every 5 minutes, and yeah, it's not that optimal. It's not that real time. So the new project that we want to deploy soon we'll have something similar like Atlas. We'll accept updates, BGP updates from our boxes, and we will update the tables in real time. So then BGPlay will be even more real time. You'll be able to see how routing changes.
Then the other thing, are there any plans to allow these probes and this infrastructure be released as kind of open source or something like that? Because why I'm asking this, In my company, we have several thousand clients, and we prefer to monitor the path to them. So basically, how we can achieve this, or are there any plans to make this task easier for us?
Right. I think you can do trace routes now, right? So you can schedule trace routes.
Yeah, but this is not so nice and shiny.
That's true. We're working on different visualization. So I think there will be a visualization with the graph. So you'll be able to see how requests are going from one point to another. So that may help. I think there are API, so you can create your measurements in the scripts if you have enough credits, internal credits, which were introduced to rate limit the number of measurements. We don't want to DDoS anybody. So you can do that, schedule measurements, yeah. I think firmware is open source of this probe. I think it's available for download from the website.
Thanks.
Nope. Thank you.